Okay, so in the last lecture we showed that the integral that's given by the Lagrangian, in fact let's write in the Lagrangian, a half y dash squared minus a half y squared dx leads to a five-dimensional algebra of vector fields that leaves this integral invariant. So that this integral is invariant and leads to the following, leads to a five-dimensional algebra, and the basis of that algebra is, and we will give the basis, the complete basis, of which we've done one or two elements last time. So we got x1 say equals d dx, and that came with the gauge term 0. Then if we chose b equal to 1, we got cos 2x d dx minus y sine 2x d dy, and the corresponding gauge term there was f2 equal to minus y squared cosine 2x, then x3, which is similar to x2, is sine 2x d dx plus y cos 2x d dy. This you would have got if you put c equal to 1 and the rest equal to 0, and the corresponding gauge term f would be a minus y squared sine 2x. x4 is the vector field cos x d dy, and the gauge function f is minus y sine x. This comes from putting d equal to 1, and when you put e equal to 1, you get sine x d dy, and the corresponding gauge function is y cos x. So there's the five-dimensional algebra of vector fields that leave invariant this integral, where your Lagrangian is a half y dash squared minus a half y squared. Okay, now let's just look a little closer and recall some aspects of this Lagrangian. If this is the Lagrangian, then the corresponding differential equation we mentioned many times is y double dash plus y equal to 0. This differential equation, if we study the vector fields that leave the differential equation invariant from the previous chapters, we would have got 8 vector fields, or one parameter Lie groups of transformations. The basis would contain 8 vector fields, and now we showed that if you look at the invariance of this Lagrangian, we end up with an algebra with basis containing 5 vector fields, dimension 5, and 8 on that side. Certainly there's a relationship between the Lagrangian of an equation and, or rather the symmetries, the vector fields that come from the Lagrangian of the equation, and the vector fields that are related to the differential equation. And this is a theorem that says that the vector fields that leave invariant your integral always form a subalgebra of the vector fields that leave invariant the corresponding Euler-Lagrange differential equation. The vector fields that leave invariant this integral, these 5 for example that we found, are called Noether symmetries. And of course these Noether symmetries we constructed with corresponding gauge functions. If we put the gauge equal to 0 in this example, we would have only found one such vector field, which is x1. The vector fields that leave the differential equation invariant, the kind of thing we did in an earlier chapter, are called Lie symmetries. So vector fields here are called Noether symmetries. Vector fields previously are called Noether symmetries. And the Noether symmetries always form a sub-algebra of the Lie symmetries. That's the first algebraic result relating the vector fields that leave invariant your integral in the calculus of variation compared with the vector fields that leave invariant the differential equation. Remember, it is this Lagrangian here that leads to this differential equation there. And this is the algebraic relationship between the invariance properties of the two things. But the vector fields that are found using the Noether symmetries, or rather the Noether symmetries, the vector fields that are found via this procedure that we just discussed, via this Lagrangian, have a special relationship to the conservation laws of the corresponding differential equation. So we will show that in fact, if we know a Lagrangian of a differential equation, here's your differential equation. If we know a Lagrangian of the differential equation, we study the invariance of the integral by this procedure that we've just discussed, find the Noether symmetries. It turns out that these Noether symmetries, by way of a formula, leads us to construct first integrals, in other words, conservation laws. And essentially, conservation laws means we can construct first integrals of the original differential equation or the corresponding differential equation. And that is the relationship then between a Lagrangian, conservation laws, and the differential equation. It turns out that if a differential equation has a different Lagrangian, it may mean it will have a different algebra on Noether symmetries. So obviously you would like to have the nicest, whatever that means, the nicest Lagrangian associated with a given differential equation. But that's not always easy to obtain. Okay, so let's just, in the context of what I just mentioned, that if we go back to the free particle differential equation, y double dashed equal to 0, that looks more like y to the n equal to 0. Let's write that a bit better. So if we have y double dashed equal to 0, this differential equation, like the previous one, has 8 Lie symmetries. Via its Lagrangian, a half y dash squared will end up with 5 Noether symmetries, and that is going to be one of your exercises, by the way. And this differential equation, of course, has, remember, alternative Lagrangians too. So the question is, if we used L dashed or L star that we mentioned earlier on, what would the Noether symmetries be then? Okay, so let's put in this as an exercise, first of all, that if L is equal to a half y dash squared with non-zero gauge, like in the example we just did, find the Noether symmetries. And remember, this Lagrangian is a Lagrangian of the differential equation y double dashed equal to 0. And secondly, if you have a Lagrangian, and this Lagrangian is the same, is a Lagrangian for the same differential equation, find the Noether symmetries. And it would be interesting if we go through that procedure to find the Noether symmetries associated with this Lagrangian, L star. L star, let's just recall, was a half y dashed squared minus 1/6 x y dashed cubed. Find the Noether symmetries of this Lagrangian, or via this Lagrangian, which is also a Lagrangian of the differential equation y double dashed equal to 0. So all of these Lagrangians mentioned here are Lagrangians related to the free particle equation y double dashed equal to 0. Okay, the next step, of course, is to state and prove the theorem that relates the vector fields that leave invariant your integral, i.e. your Noether symmetries, to the construction of conservation laws. And I mentioned then that there is a theorem, and this is the ultimate Noether theorem, that says that every Noether symmetry can be used, of course with its corresponding gauge function, can be used to construct a conservation law for the differential equation. So in other words, if you have 5 Noether symmetries coming from this Lagrangian for this differential equation, you will construct 5 conservation laws for this differential equation. So this is a rather short lecture, and in the next lecture we're going to show how, or rather state and prove the theorem that relates the Noether symmetries to the construction via formula of a conservation law.